Ah, ah. That's nothing. Thank you.
Because you told me all that. I nearly know I didn't feel it. Did you read something in that or? I didn't even talk there. It's just the detail of it. It's not the whole thing.
Is it possible? Or is it like?
Is it?
Is it visible?
It could be, hopefully, they're checking, yeah, it's fine. It's just that,
Or should we?
yeah, we have 1 hour.
Yeah. No, none of that.
Yeah, I think.
Yes. Ya o dünyalar black falan yani ben biraz sınavlar ya olsun ya o kadar şey olsa bu
Tabii bir buradan daha
bilmem daha yani
Yeah, I went to that same Saturday. Yeah, there's a.
I'll tell you, you were thinking to come somewhere, I took, I think, but I really didn't talk where I felt it. I wanted to know the window buttons.
Should I be there? Like, there is a nice thing like, can you see some? Can you see?
The picture here. I don't, I'm sorry, yeah, it is. Yeah, it looks good. Yeah. Yeah, yeah, yes. There you're around the middle, you can even come closer. Not very far.
Okay. So we get started.
Yeah. Next step is
Okay. So, welcome everyone. We're very happy to have Debarati Chatterjee here today. So Professor Chatterjee did her the PhD in India and then went to a lot of places, to Heidelberg, and then to France, to the Paris Observatory, and then to Normandy University, and then I think to Heidelberg once more at some point. Right?
I was in
Oh,
Frankfurt.
Frankfurt, sorry. Yeah, right. Frankfurt, and now for some time she's been to the Inter-University Center for Astronomy and Astrophysics in Pune, in India, and we're very happy to have her here. Thank you so much.
Thank you very much. First of all, to Tolga and Kai for having me here. I love this city and I've always had a really love. So I think I will do first. Okay. So yeah, I'm currently professor of astrophysics in India, mostly working within the LIGO collaboration. As you can see, I'm a member of LIGO scientific collaboration, the LIGO India scientific collaboration, which work on gravitational waves across 18 countries. I'm also a member of some other collaborations like MUSES. So this is also an American collaboration, which works on different aspects of dense matter. So I will tell you a little bit more about this as I go on. Feel free to stop me and ask questions. Today my focus will be mostly on gravitational waves, particularly why this emerging field of astronomy is so important and so exciting, and how it is helping us to understand fundamental physics. So this is like a topic of this talk. So
Yeah. Can you try again?
is this right?
It's actually connected.
Yes, yes.
Now it will. Yeah.
So thank you. So yeah, so why do we, so when we are talking about gravitational, so particularly we want to talk about compact stars. So what are these objects? So basically, I'm talking about these objects, so white dwarfs, neutron stars, and black holes. Particularly because these are extremely compact and great gravitational resources. So these are not really stars, so they are objects which are formed at the end point of evolution of stars. So light stars like the sun, they end up as white dwarfs, and more massive stars, they end up through supernova explosions to compact objects such as a neutron star or a black hole. So why do we call them compact? Well, if you look at the numbers, so their masses and radii as compared to the Earth, you will see that their compactness or surface gravity is very high. They are extremely small and ultra dense. In fact, neutron stars are the densest objects in the universe, and therefore they serve as essentially as cosmic laboratories to study fundamental physics. So this is why we are interested. And so just to show you an animation of how this works, so you have a nuclear fusion inside the stars. So for massive stars, this goes on until iron is formed at the center. There is no more fusion happening, so there is a supernova explosion, and the dense core ends up as a neutron star. And this is what we are talking about. So neutron stars were, of course, first discovered in very serendipitously by Jocelyn Bell. So a young PhD student at Cambridge University, when she was looking for radio signals coming from distant quasars. So she came across some scribbles in the radio frequencies, and these were not understood at the time. People even thought they were coming from aliens and so on. But now we know that these are nothing but periodic signals coming very, very periodically from like neutron stars, which are very compact, and therefore every time the beam crosses the direction of the Earth, we get the very periodic radio signals. Now, of course, we can observe neutron stars throughout the electromagnetic spectrum, all the way from gamma rays, X-rays to infrared, microwave, and radio. And with the help of a large number of space-based and ground-based detectors. Here you can see the Crab Nebula is seen through multi-messenger observations. And so you see here in radio, infrared, visible light, you only see the gaseous nebula, but in X-rays, you can also see the compact star, neutron star sitting at the center. So why the other thing is black holes, of course, and black holes are much more difficult to observe because, of course, by definition, black holes don't allow any light to escape their surface. So the only way of observing them is when a hot gas is getting sucked into the black hole and this lights up, and we can observe this in electromagnetic radiation. So our understanding of like our detection of these compact objects is only limited to these kind of observations because there is no light being emitted like normal stars from them. So here you may have seen these in the news, the first ever image of a black hole. This happened from recently in 2019 and 2021. We could also observe the polarized light coming out of black holes from such electromagnetic signals. And recently 22 and 24, so we also had the Sagittarius A black hole, this one at the center of the galaxy. And so also radiation coming from it and polarization of light, which tells us about the magnetic field of the black hole sitting at the center of our own galaxy. So these are great observations, great developments in electromagnetic observations. But so this also happened with the help of a large collaboration of telescopes around the world, which is collectively called the Event Horizon Telescope. So now let's see how gravitational waves is helping us to understand these compact objects. So gravitational waves, can we maybe I will try to. Yeah.
This is key.
So how does gravitational waves help us? So 100 years ago, back in 1915, Albert Einstein's theory of general relativity changed our perception of gravity. And therefore, it now said that gravity is no longer the older concept of just a force between objects, but a curvature resulting from the curvature of space-time around massive objects. So this meant that the more massive and more ultra-dense the object, it's going to bend space-time around. So naturally, a natural result of this theory is that if you have any perturbation happening between these massive objects, massive cosmic objects, like a collision of black holes or a collision of neutron stars or a perturbation inside them, then these would give out these ripples across the space-time. And if we can observe them, then we can say something about their internal properties. So this was very exciting because compact stars, like I said, it's very challenging to observe them in electromagnetic radiation. They don't generally emit light like normal stars. So the next idea, of course, that people started to explore was to look for gravitational waves coming from supermassive black holes or from neutron stars. So so not only neutrons, so not only collision, there can also be other forms of gravitational wave emission. So we can classify them very broadly into short duration and long duration. So the ones which are like mergers of two black holes or two neutron stars, these are extremely short. And there can also be long duration continuous gravitational waves. I will tell you a little more about it towards the end. And there can also be other sources of gravitational waves. For example, if there is a burst kind of phenomena, like say the supernova explosion that I was just talking about. So these could also give out a burst of gravitational waves. And these would be, again, short duration ones. Other than that, there is also a background of gravitational wave emission in, like, we have radio background in the universe. Similarly, there will be a noise background called a stochastic background coming from like the background of all the different gravitational wave sources. So now once Einstein proposed this, of course, people started to look for gravitational waves. I'm not even talking about the early attempts to detect gravitational waves. Like the first ever attempt was made by Weber. So Weber built a bar detector, and there was a false claim that he observed gravitational waves. So thankfully, that led to a lot of excitement. But gravitational waves were not detected. The reason is that they are extremely small. So I will come to that in the next slide. But what happened is that there were many designs for gravitational wave detectors, bar detectors, spherical detectors, and so on. There was another class of detectors called the laser interferometer gravitational wave observatory, shortly called LIGO. So the idea is that we have these tabletop interferometers that we use in optical laboratories. So the same kind of interferometer where you have laser lights coming out from a source, it is split across perpendicular direction along two arms, and then they reflect back at the center, form a fringe. So this is the setup of an interferometer, and now if a disturbance passes through it, like the gravitational waves, it would now distort this geometry, and we would detect a phase change. So that is how we know gravitational waves are passing through it. Now the only problem was, so I will show you in the next slide, that the change in this length is extremely small compared to other optics experiment, tabletop interferometers. So the change in length to a given length is around 10 to the minus 23, 10 to the minus 24. So you can imagine it's like, detecting a hair on the surface of the moon. It's extremely different. So this was almost thought to be impossible at that time. And so the idea was to build the same interferometric design, but to amplify the effect, these arms are 4 kilometers long. So that is the design of LIGO. So this is the LIGO Livingston and the LIGO Hanford detectors, which are across the two ends of the US. And the third one is in the border of Italy and France, called Borgo. This is a slightly smaller 3-kilometer arm. So, well, this was the initial LIGO design. So people were, trying to achieve already. You can see that this is an extremely difficult task to have a sensitivity which is 10 to the minus 23 to detect a change in length of that order. So this is the theoretical idea of where you expect the sources to be. So these are frequencies. So LIGO is actually here. So you can see here. So this is actually the initial LIGO, so the one which is written LIGO. So this had initially a sensitivity of 10 to the minus 21 approximately. So I had several colleagues working during that time in initial LIGO. We did not observe anything. And of course, like the government said, okay, maybe we don't give you any funding because you will never observe anything. It is considered impossible. And they would celebrate cutting a cake every time they went slightly better in sensitivity curve. So this happened for 10 years. Then the improvement happened in the sensitivity to advanced LIGO. So this was like through a lot of technological development. And the reason why the curve looks like this is actually shown here. So the strain, and this is again the frequency. So these are limited by many different noise sources. So you can understand you're trying to detect a change in length, which is that small, but you have cars going around, you have aeroplanes, you have heavy machinery. So it is already the detectors are built in an isolated area, but there are always disturbances. So to cut them down, so there are seismic noise, to cut them down, so they are built in tunnels, suspended through mechanics, very sophisticated mechanical arrangement. There are these very high precision laser beams going through the tunnel. Then you have quantum noise. Quantum noise was a problem until very recently. LIGO came up with a new technology called quantum squeezing, which has been developed just for to circumvent this kind of problem at low frequencies and so on. So all these things limit the detection capability at low and high frequency. Therefore, it is shaped kind of like this. But the highest sensitivity is around kilohertz frequency. So there we expect to see gravitational waves from pulsars, supernovae, or also some light black holes. So now, through, like I was saying, so from initial LIGO design to advanced LIGO design to 10 years or more, about 15 years, and through a lot of multidisciplinary technology development in optics, lasers, vacuum technology, mechanics, and feedback and control systems. So you can see that this is like not just expertise of one field, so it required combined effort from a large number of multidisciplinary domains from with which they could actually achieve the design sensitivity that they were aiming for, like 10 to the minus 23. So this happened around 2015, and as soon as the LIGO was switched on, the first gravitational wave was detected. So earlier already we had an indirect evidence that gravitational waves exist, and this came from binary neutron star meter. So it is called the Hulse-Taylor pulsar because they were discovered by Joseph Taylor and Russell Hulse back in 1974. And the idea was that they observed these two neutron stars going around each other. And because they are emitting gravitational waves, they are coming closer and closer. So they said that if general relativity of Albert Einstein is true, they would follow, their trajectory would exactly follow the curve predicted by Einstein. So they went on and tested this over several years, and it was found to exactly follow the general relativity prediction, which means that this system of binary neutron stars was actually emitting gravitational waves and coming closer and closer together. So they were given the Nobel Prize for Physics in 1993 for, not only this, there were several discoveries associated with this binary pulsar system, but this was also one of them, the indirect evidence that gravitational waves exist. So of course, after that, like I was telling you through the advancement of all these fields, now that the detection sensitivity had been reached. So 2015, the LIGO, advanced LIGO detector was switched on, and as soon as it was switched on, the first detection happened. So this was again, it was announced a bit later because people were, I already talked to Gabriela Gonzalez, who was the head at that time, and she said, we were very, very careful to check that this is not a noise source coming from some, you can have some free noises. So it was not the case. So the reason they could say this for sure that this was coming from black holes is that it has a very typical signal, which is called a chirp signal, like the chirp of a bird. It goes like to shrill high frequencies when the black holes come closer together and ultimately merge. So this is like the in spiral phase, and ultimately when they merge, there is a rise in frequency. And this chirp signal was exactly observed at LIGO Livingston and LIGO Hanford detectors, just a little after each other. And so this was, of course, the first detection of gravitational waves coming from a system of heavy binary black holes. So this happened, so we are celebrating this year the 10th anniversary of this event on 14th September, and it was announced on 11th February the next year. So now that we know that gravitational waves exist, then this was of course the first discovery, but after that it was followed by many more. I will show you what the current status of this is like. But now it was exciting for people doing fundamental physics because now you can detect gravitational waves coming from the interior of these objects, and these gravitational waves carry information about their interior and their interior properties that otherwise you could not, with electromagnetic radiation, it was not enough to observe. You could only observe some surface properties. So neutron stars. So I will talk a little bit more about this because this is my field of research. So neutron stars are excellent gravitational wave sources, again, because they are the most dense object in the universe. Before less than black holes. And so if there is any kind of non-axis symmetric disturbance in a neutron star, they will emit gravitational waves. So that means if you have a collision of two neutron stars, we already know this from Hulse-Taylor pulsar, that they emit gravitational waves. You could also have many other phenomena in neutron stars. For example, if there are phenomena called glitches. So neutron stars rotate very, very periodically, but we see in their rotation frequency, sometimes they undergo glitches. So some systems like Vela pulsar, it shows very, very regular and large glitches. So those would give off large, sharp gravitational wave signals, those kind of signals. Also, if you have very highly magnetized neutron stars called magnetars. They can also show features like flares and outbursts like you see in the sun. And that could also show up as burst gravitational wave signals. Not only that, so continuous sources. So if you have some kind of deformation on the surface of a neutron star, so say there is a small, I mean, it is called a mountain. Well, ideally, it's just like a little a centimeter high. The Everest would be a few centimeters on the surface of a neutron star because of the strong gravity. But that deformation is enough to produce gravitational waves. So a rotating deformed neutron star will also give out gravitational waves for many years, and this could also be detected eventually. Also, like I was talking about, magnetars, very strong magnetic fields can deform them from spherical shape into a cigar-like thing. And if this is rotating, this could also interact. So this is very exciting. So neutron stars, like otherwise, I will tell you like with electromagnetic what we can do, but gravitational waves is now a new way of probing their interior. So just to talk about like what we know about neutron stars and why we want to see gravitational waves from them. So the thing is, neutron stars, like I said, they are ultra dense. They are basically the densest objects in the universe. And let's compare them with what we know from terrestrial experiments. So ideally, if we want to know what is, what everything is composed of around us, we go to perform some nuclear experiments to see, okay, what are atoms nuclei composed of. And nuclear experiments gives us information about dense matter at cold temperatures, laboratory temperatures, and close to the nuclear density, which is called the saturation nuclear density, around 10 to the power 14 gram per centimeter cube. And also most of the nuclei we see on Earth, they have similar number of neutrons and protons. The reason is, so if you see here, this is from nuclear physics, so the proton number versus the neutron number, so this is the line of stability. So most of the nuclei we find in nature are along this line. There are a few experiments, like when I was in France, so we had an experiment in Daniel. I solved, so this tests halo nuclei like very far from the stability, so you can probe a little bit neutron-rich nuclei. But neutron stars, can you imagine they are made up entirely of neutrons, mostly of neutrons. So that kind of system, we have no idea. It's ultra dense and it is full of neutrons, so we don't know how to treat them with just knowledge from nuclear experiments. So nuclear experiments does give us some properties which are close to the nuclear saturation density from observation of giant resonances. There is something called neutron skin thickness, so the difference between neutron and proton radii, and those giant dipole resonance, monopole resonance, dipole polarizability. So the different nuclear experiments also give us some information of properties close to nuclear density. The other thing we look for to probe matter composition is particle accelerators, right? So when we look at particle accelerators, heavy ion collision experiments, they tell us about hot and dense matter as high as a few times saturation nuclear density. They are also having the same number of neutrons and protons, but the modeling of, to infer properties of cold matter from this hot matter is difficult because the transport models which are involved, they are still not in agreement with each other and so on. But this is all the information we have from terrestrial experiments about fundamental physics. And another very interesting thing we see in heavy ion collisions is that the appearance of heavier particles which we don't see otherwise around us. So everything around us is made up of neutrons, protons, which are again made up of up and down quarks, the lightest quarks. But heavy ion collisions also see the appearance of the next higher quark. So this we don't see in nature around us. Now we think that if such strange matter exists, so they give rise to hypernuclei where you can replace some of the UD quarks by S quarks, and you can compose a lot of exotic matter like hyperons and kaons and so on. So these are seen in these particle accelerator experiments. So now, with all this information we have from nuclear and heavy ion experiments, we can try to paint a picture of neutron stars, like what its interior could look like. Again, this is guess because we cannot go and see what's happening. So neutron stars, if I forgot to tell you in the beginning, so they have masses around 1 to 2 times that of the sun, but within a very small radius of only 10 kilometers. So you're shrinking the sun to size of the city. So if you do back of the envelope calculation, it tells you that the densities inside can shoot up to 10 times nuclear saturation density that you see in the experiments. So that means you are spanning a huge range of densities all the way from nuclei at the surface, which are iron nuclei that were formed during the supernova explosion, but the interior you can go up to 10 times saturation density. So that means you are encountering many different forms of matter. So that's why it's very difficult to model these objects, because you are going from nuclear regime to particle physics regime with such high densities. So if you look at the cross section, you start with some nuclei and electrons, you enter the outer crust, and then you start there are so many neutrons that you start to have like a neutron sea with nuclei. The density increases even further. Now these nuclei start to become deformed, and they are called pasta phases. This is not the Turkish pasta, the Italian pasta. the pasta phases, because they look like spaghetti and lasagna. They have actually a lot of some fancy names. I don't even know what actual pasta looks like, but they have very deformed nuclei in this phase. And ultimately, all this melts into a homogeneous fluid maximally filled with neutrons and a small fraction of protons and electrons for chemical equilibrium and charge neutrality. So now this is mostly composing what we think is a neutron. That's why we call it a neutron star. It's mostly this big ball of neutrons with a crust around. Now, when we're crossing 2 to 3 times nuclear density, this is an entire mystery, because we don't know what's happening. This is already beyond our knowledge of nuclear and particle experiments. So we just can do some guesswork by extrapolating our information to the unknown regimes. So what we think is all these particles that we see in particle accelerators like hyperons, kaons, they could appear in the center. And of course, theory can give you many other possibilities. I'm not even going to discuss that, like color superconducting quark matter. You can have deconfined quark matter inside and so on. So a lot of possibilities are there that can appear inside this. And there is no way of probing this, with our terrestrial knowledge. So another interesting fact why we want to study this is summarized in this figure to see that nuclear particle experiments give us different information than what we get from neutron stars. So here, this is a figure of the QCD phase diagram for chromodynamics, which is the theory of dense matter. So here you have temperature and density. And nuclear, so this is in terms of saturation nuclear density. So everything in nuclear experiments is around here, 1. So this is in terms of nuclear saturation density. So cold and dense matter. Then heavy ions are hot and dense matter, going to 2 to 3 times saturation density. So they are giving us information here. But neutron stars, which are neutron rich, cold and dense, are lying on a different plane. So they are all like a jigsaw puzzle from which we can get some information, but we also need to extrapolate it to some other unknown domains. But again, we don't know because we need some observations to test them, right? So let's look at what observations we already have. So I already talked about electromagnetic observations. So what we do is, in order to go to something observable, we need a model that connects the interior composition to something observable that we can look at with telescopes. So that means this is called an equation of state. So like, ideal gases have equation of state connecting pressure, temperature, density. These are zero temperature, they are cold systems, so they have only pressure density relationship, the equation of state. And from the equation of state, if we solve the hydrostatic equilibrium condition, which means the gravity is balancing the pressure, so we can find its structure like mass, radius, etc. And we can actually now go and observe with telescopes and check whether which kind of observation matches our theory. So for example, here is a fake pressure density cartoon. And this connects, it's like a map going to a mass radius figure. And now we measure the mass and radius and see which of the composition matches that. So this is something we can try to do. Now, all these observations I talked about, so we can observe neutron stars across the electromagnetic spectrum, and they give us a lot of information like its spin period, which is very periodic, its mass from binary systems, moment of inertia from precision. Spectral lines can give us the mass to radius ratio, which is called compactness, and so on. And then we can try to constrain our models. So binary neutron stars are pretty good, like for measurement of masses, because we can not only measure Keplerian parameters, so Kepler's laws, but also the next order correction, post-Keplerian parameters. From that, we can ideally, derive all the masses of neutron stars. So here is like a chart, a slightly older one, of all these measured masses of neutron stars with their uncertainties. They mostly fall around a 1.4, like 1.5 solar mass value, but there are a few which are very massive. So these, I will tell you why these are important. Radii are much more difficult to observe because radii you can only measure for isolated stars and from the thermal emission. They need some modeling and they are dependent on models. It's not very easy to extract the information. But recently, with the launch of the NICER mission from NASA, the Neutron Star Interior Composition Explorer mission, you can now, with the help of a technique called pulse profile modeling, which means that you see hotspots on the surface of a neutron star, even when they are going behind the star because of relativistic effects, and you can measure the radii very accurately. So now what we can do is you have a zoo of these pressure density relationships or the equation of state. From that, you can also obtain a zoo of mass radius curves. Then on top of that, now you can impose constraints from actual observations, which you get from these data. And then you see which of your models can actually satisfy, otherwise you can reject. So that is, of course, improving our understanding of the interior composition of neutron stars. Mostly we were confined to this kind of observation. But now with gravitational waves, let's see what we do. So the first detection of binary neutron star merger came in 2017. So soon after the first detection, 2015, came the first discovery of a binary neutron star merger. And what was exciting is that this event called GW170817, 17th of August 2017, not only the gravitational waves were detected, but also you can see that all these electromagnetic counterparts were also detected, which means that the same event was seen. Again, let me play this for you. So the same event was actually seen in radio frequencies, in gamma rays, in X-rays, and so on. So we were really lucky with the first discovery because it gave us a lot of information from the first discovery set. I think people are still working on some of the interpretations. There was so much information about it. So for example, the same event, which was seen by LIGO and Virgo, again, a sharp rise in the signal, was seen by the Fermi and integral gamma ray telescopes, which were observing at that time. And they found bursts soon after this event. And these are now understood to be short gamma ray bursts. So earlier there was a speculation whether short gamma ray bursts are related to binary neutron star merger. So this one event confirmed that this was actually the case. Not only that, so there was also observation of kilonova. Kilonova means like a supernova, but the luminosity is slightly smaller. So this was observed at optical frequencies. You also had radio observations from VLA, X-ray, from Chandra, and so on. So many different properties were identified from this one single event. Not only that, so this actually was the funniest. So what was observed was spectral absorption spectra of cesium and tellurium coming from the what should I say, the electromagnetic counterpart. And it is known that this cesium and tellurium are formed in a similar way as gold, silver, platinum. So this means it confirms that this type of process, a formation of elements called R process nucleosynthesis happens inside neutron stars. So funnily, this got a lot of attention on the media because people were like, oh, so all the gold, silver, platinum comes from neutron star mergers. So well, whatever gets scientists' attention is good. So this was, yeah, again, it was now understood that this process of our process, nucleosynthesis, happens inside neutron star molecules. So of course, this was also very exciting for nuclear physicists. And also for equation of state, this was vital because of information we get from this single event. So during the merger, so this is the inspiral phase. This is what the waveform looks like. So this is the inspiral phase when the neutron stars are coming closer together. They merge, so there is a peak in the signal, and then there is what is called a ring down, which means it's like ringing like a bell, and it slowly, stops. So this part can be observed by LIGO. This part actually cannot. But from the inspiral signal, what happens is these neutron stars are actually deforming each other. So like tides, they are deforming each other, and that deformation is related to the compactness of the star, its mass and radius. Therefore, it means that it gives you an independent way to measure its mass and radius. So that was great because earlier there was no other way of observing them other than electromagnetic radiation, which had a lot of uncertainty. So now this gave us some extra contour plots on the mass and radius, which helps us now to correct our theories, which of the theories are correct. So I'll tell you a little bit about my group. So these are my students at IUSPA, and what we do here is just in a couple of slides. What we do is basically we model the interior of neutron stars. So that means we include information from nuclear physics, particle physics, phase transitions from normal matter to quark matter, whatever information we can get from terrestrial experiments, combining all of them to construct the models. Then we construct their global structure with the help of models or numerical simulations. And we include effects like general relativity, hydrodynamics, magnetic field, in order to get something which is observable. And the other thing we do is then to check how these can affect the gravitational wave function. So this I will tell you a little bit more about just to give you a flavor of what kind of work we are doing. But so whether it's a merger or whether it's an oscillation of a neutron star, you can get information. You can get information about the interior properties of neutron star from all these sources. So this is what we do for research. So to give you one glimpse, so I already showed you this plot, the same QCD phase diagram of the temperature and density of everything. And then here you have nuclear theory at low density. So currently there is a lot of development of state-of-the-art nuclear theory calculations, which are calculating term by term the expansion and how nuclei behave in dense matter. So this is some information we have at low densities. Then you have some information coming from heavy ion experiments at intermediate densities, but this is not matter. And then you can now add information coming from this maximum neutron star mass, which is close to 2 solar mass, information from gravitational radiation, the data from NICER, and so on. So you can combine all of this, and that gives you a way to restrict the models that you have. So this is something that we have worked on for different types of matter inside neutron stars. The other thing we do, we have concentrated on in the last years is what is called astroseismology. So this is very interesting because this is very similar to earthquakes actually. So earthquakes, if you want to know what is at the center of the earth, so you cannot go and measure it, right? So you look at properties of the earthquakes. Similarly, you have seismology, stellar seismology as well, astroseismology. So stars also undergo fluid oscillations, just the same way that you see in experiments. And in the sun also you have helioseismology. So this is a good way of observing, these oscillation modes tell you about the density and other properties of the stars. So here maybe you can see that these are like some oscillation modes, and these are also some oscillation modes. So you can have different types of oscillation modes in neutron stars. They depending on what is the restoring force bringing them back to equilibrium. You can classify them in different modes. So for example, F modes and P modes, these are nothing but restored by pressure. So these are acoustic modes. Then you have G modes, which are restored by buoyancy. So they are, so all of this actually give you information about their interior. So for example, G modes are susceptible if you have any change in density or composition, then G modes are very sensitive to that. The other one, F and P modes, so these are sensitive to the density, the interior density. R modes are rotational modes, so very similar to the Coriolis force that we have on Earth. So these R modes can also become unstable, and they are very interesting because we think that R modes are the mechanism through which newly born rapidly rotating neutron stars actually slow down, and we observe them as slow down. So R modes are also very interesting. So these are also found in other stars, stellar astrophysics. What neutron stars have in addition are also space-time modes because they are very strongly relativistic. And these are very similar to black hole quasi-modes. So you can actually observe many of these modes. So several of them are in the kilohertz band, which LIGO is sensitive to. So F modes, for example, are in the kilohertz band. These are slightly lower in the hertz regime. So you can try to detect these oscillation modes. It is more difficult, of course, because unless they are triggered during the in-spiral, it is going to be difficult if they are low amplitude. But anyway, so this is very exciting. So we did several studies with different models to understand how these F modes would be affected by their interior composition. And if we can observe F modes with gravitational waves, they have not yet been detected, how we can constrain our mind from that. So for example, we took the case of the Vela pulsar, which I told you is very strongly glitching. So if a glitch in the Vela pulsar triggers these F mode oscillations, then can we say something about, so this is, for example, a single event, or if we have multiple glitches in the Vela pulsar, whether we can constrain the equation of state. So you can see here it becomes narrower, and the mass versus radius also, the curves become narrower with more and more of observation. So this is something we are probing so that if F modes are detected, we can say something about the interior mode. Another interesting possibility, again, this is exciting because people don't know if they exist, but if they do, it's something very exciting. So people think that if you have quark matter, so everything around us is made up of quarks, but they are bound. But we think that at very high densities, these quarks could become deconfined. And this phase transition could be either strong or a mixed phase. So we also proposed one way of testing which is the case. So if you have a strong phase transition, you can actually produce a different branch in the mass radius curve, which is interesting because that means you can form a different star, we call it a twin star because it has the same mass as a neutron star, but smaller radius. So we tested whether F modes can actually tell you whether you are seeing a neutron star or its twin. So these are exciting possibilities because if we actually observe a twin star, we can say that this strong phase transition is happening. We also tested the other possibility. So I was telling you that the post-merger regime is not observed because they are outside the LIGO band. They are at higher frequencies. But we also probed that whether, so if you can actually get the signal from the post-merger phase, then you can say something about the hot neutron star equation of state, because post-merger phase, the neutron star which is formed after the merger, it's hot, it's rapidly rotating, differentially rotating, strongly magnetized. So this is very exciting for the equation of state because it tells you something about all these exotic, these extreme properties of matter. So we also tested what happens in these scenarios, like post-merger or even in the proto-neutron star phase. It's a hot neutron star just formed from supernova. It's slowing down and it is in a hot phase. So if there are oscillations excited in this proto-neutron star or oscillations in the post-merger remnant, then how that would be affected and how we can get gravitational waves from them, telling us a little bit about the hot neutron star matter. So these are some things that we probed. Another exciting thing is G-modes. So I told you that G-modes are again lower frequency. So they are around 500 to 900 frequency. So these are the low end of the LIGO band. But so what we found that depending on the interior composition, you can see if there are hyperons, for example, you can see a sharp shift in the slope of the frequency. So that is an indicator of strange matter inside neutron stars. So there are different ways of probing through oscillation modes what can be the interior composition. Another possibility which we also explored a lot is dark matter. So this is exciting because we know that dark matter is there abundantly. That is what is our understanding now, that dark matter could be present abundantly in the galactic halos. So if that is the case, you can expect to have dark matter trapped inside the stars. So either they could be accreted or they could also be some possibility, like some experiments indicate that neutrons could decay via a dark channel, forming dark matter inside neutrons. So if that is the case, so you could have either a dark matter core in the neutron star or even a dark matter halo outside the star. So that means if that is present, it can affect your mass and radius. And so we will be interpreting wrongly. What we think is normal matter is actually dark matter at next neutron star. So we tested how the presence of dark matter can affect these oscillation modes or observation of the structure around them. So yeah, we did several studies on this as well. So this is the last thing. So I told you about neutron stars. If they are, they have a deformation and they are rapidly rotating, they could give off gravitational waves as continuous sources for several years. They are less free amplitude because they are isolated sources. But if we can observe for a longer time, we should be able to say something about their if we can detect them, we can say something about their interior. For example, if you have a mountain or a bump on the surface, this could give you an information about its crustal properties. So such mountains could be formed either during birth from a supernova or accretion, if it is accreting material from a companion star, or if there is a strong magnetic field. So all this could produce a mountain. And if we do observe gravitational waves from such a bump, then we know how much is the crustal force that can be sustained to a neutron star. Not only that, I just told you you can have these unstable rotational modes. So this could also be interesting to tell us about viscosities inside the star. The viscosities also depend on the interior composition. Then if you have large magnetic field, they could tell you about the field amplitude or its configuration, and so on. So these are also being searched for in the LIGO collaboration. Unfortunately, we have not detected them. There are different searches. So for example, targeted searches, which means we know there is a neutron star. So we target like that star. So say for example, we know Crab pulsar, Vela pulsar, Cassiopeia A. So we look at these sources and see if we can see any gravitational waves. Unfortunately, we have not. Directed sources, so we don't know we don't see a neutron star, but we, for example, see a supernova remnant. So we expect there could be a neutron star sitting there, or globular clusters, which typically have large number of neutron stars. So people look for signals from those sources. There are also some blind searches of all sky, all frequency. I don't know if you've heard of the Einstein at Home project. So this is a very interesting one because it can be actually done on, it's a citizen science project, so it can be done on your computer as well. So people use their computers across the world to, with the Einstein at Home project to search for, in all sky, in all frequencies, if there is any continuous gravitational wave coming. So at the end of several searches, there are a lot of candidates. So here you can see all these stars, they actually which are possible candidates for continuous sources. Unfortunately, we have not observed them, observed gravitational waves, but that also gives you a limit on the ellipticity. Here you can't see the figure, I think, but ellipticity as a function of frequency, you can also say how much is the deformation. So that means that when you do observe continuous waves, it tells you that the surface of the neutron star must be very smooth. And our conjecture now that it is getting smoother and smoother. So I don't know, maybe there is a fault in the way we are searching, or neutron star where it should be smooth. So that's the end. So basically, this is the last public data that was from the LIGO collaboration. So it's called the GWTC3 catalog. So each observing run has a name, O1, O2, O3, and each observing run continues for like 1 or 2 years. In between, there is an engineering run when you upgrade your instruments, and then there is a run again. So we are at the 4th observing run, I will tell you. So this is the last public catalog. So these actually are figures of masses of these. Most of these are binary black holes. Only one binary neutron star system. And there are a couple of neutron star black hole systems which were discovered. Here is a kind of summary of that in one plot. So I don't know if you can see. So these are like 125 to 200 in solar masses. The x-axis is nothing. This is just for symmetry. So in this figure, actually, so these, let me talk about the black holes first. So black holes, the electromagnetic black holes, I don't know if you can see the red lines, they are the ones which were discovered through electromagnetic waves. So like those, like the hot raining around black holes and so on. So we had the idea that, okay, black holes can be as massive as between 3 to 20 times the sun. So that was our idea. So now let's see with LIGO Virgo black holes, this is the third observing one. We saw black holes anywhere between 3 or even lower to 200 times that of the sun. So now this is again a challenge for theorists to explain how they are, how you can get such massive neutron stars or such massive black holes or so light black holes. There are a lot of questions which are arising. We see here, although, that these arrows actually point to the fact that these collisions, so say here is a black hole, here is another black hole, they collide to form a more massive black hole. So we can see that it does, like this collision of black holes does help to make more massive black holes, but there are a lot of questions around them. So this is great for cosmology and astrophysics. Neutron stars also. Neutron stars earlier, so electromagnetic radiation told us you could have neutron stars as massive as 1 to about 2 point, almost a little above 2 solar masses. That's what we have observed. Now, actually, so earlier we thought black holes and neutron stars, there is something like a mass gap between them. So black holes are not lighter than 2.5 and neutron stars are not more massive. Now, LIGO Virgo has found objects which are sitting right in the middle of the mass. So the question is, are these very light black holes? How are they formed? Are they very massive neutron stars? How are they being stable? Because they would also disrupt, or they would collapse if they are so massive. So maybe they are dark matter admixed neutron stars. So people don't know. Actually, these are open questions. People are trying different possibilities to see what these objects could be. So finally the status. So we are at the 4th, almost at the end of the 4th observing run. The O4C run is going on actually right now. So with each observing run, you can see here that you are looking further and further out into the universe. And with each sensitivity, with each observing run, the sensitivity curve is getting deeper and deeper. So that means you are more sensitive, you observe more sources, you're looking out more into the universe. And you're looking at more sources. So here you see that in the O3 catalog, we had 100. We already reached 200 candidates in O4. So the number of candidates is going up very sharply. We see more and more objects. Most of these are black holes, though. We did not find another neutron star system. Well, don't ask me why, because people are still debating about why they don't see as many neutron stars. So a little bit about the upcoming situation of gravitational wave network. So this is the current gravitational wave map, the 2 LIGO, Hanford and Livingston observatories I told you about across the US. There is the Virgo detector in a border of France and Italy. There is a Geo 600. This is very small, actually, 600 meters. It is not used for really observation, but for texting technologies. It was one of the oldest ones. A new detector has come up in Pagra, the site of Kamio, where the neutrino detector was there. But unfortunately, so Kagra has not reached until now the design sensitivity. They had some issues with testing a new cryogenic technology. They took too many risks, so right now they are still not at the right sensitivity. The next one to join the block is LIGO India. So LIGO India is actually the same as the other two LIGO detectors, exactly the same. And they are going to be put here in this location. And so I'll tell you a little bit more about the project. So IUPA, my institute, is the one responsible for the science part. The others are responsible for the optics and lasers and so on. And DCSM is the one responsible for construction of the project. It is coming up in the mostly, this is Maharashtra where my institute is. And this is kind of in the east part. So ideally, you can imagine it is almost at the center of it. And the reason for choosing this location is many. So firstly, because it's central, it is not in any of the border regions, like which might have issues with surrounding countries. It is in a flat land, not in the Himalayas, not on the ocean. It is in a relatively seismically calm zone. It does not have heavy industry around it. It's slightly like in the middle of nowhere. So this was ideally located for this. And also it's very well connected with by road to other cities. So the reason for building LIGO is many. I will tell you the scientific part, but also because there are many institutes in India, 17 right now, which are involved in the LIGO collaboration. They do scientific contributions to these, and they are interested in having a, since there is already a gravitational wave community existing there, they want to have a detector from which they can also, do research. So this is the LIGO India scientific collaboration. And the scientific reason, the most important motivation for the LIGO project is this, that you may know that even for GPS, you need 3 satellites at least to exactly pinpoint where your accurate location is. So with the 2 LIGO detectors, this is not possible. Virgo also does not have the same sensitivity because it's a 3-kilometer one. Thanks to Virgo, you can see here the GW170817, that binary neutron star merger, was found. And the reason we found all those electromagnetic counterparts opening this new field of multi-messenger astronomy was because Virgo was active at that time. So the third detector really helps in identifying the location in the sky where you can point your electromagnetic telescopes, and it helps you to get information. So this was possible for that system, but as you can see for the other ones where you had LIGO and Virgo only, you have a large uncertainty in the sky. So you don't know where to point your telescope, you don't get the electromagnetic observation. So now here is a comparison. There are actually several papers out on this topic. I'm not citing them here, but this is like here you can, I don't know if you can see here is like this banana shaped curve is the uncertainty if you have only LIGO detectors, and adding LIGO India to it shrinks it to a point, right, essentially. So this tells you that this is great for multi-messenger astronomy. For whatever source you are detecting in gravitational waves, you can detect the electromagnetic counterparts with the help of LIGO there. So not only, so there are some papers out right now. I'll tell you a little bit about future detectors. So LIGO India will also help future detectors for identifying location, even if it is not at the design center.
Still the 50 result, right?
It's a few degrees, yeah, but I think it's up to 9-fold. Some,
Sure.
yeah. Yeah. And yeah, there are also other papers which talk about like some blind spots which can't be seen with LIGO detectors only, but there are almost no blind spots with the third detector. So there are a lot of scientific advantages. Beyond, so LIGO India is what is called a 2.5 generation because it's slightly better than what we have right now. But so I forgot to tell you that so LIGO India will join in 05 run. So we are now finishing the 04, and 05 is where LIGO India is supposed to step in. But in the future, we have plans for even bigger, better detectors, which are called third generation 3G. And here, actually, on the right, you can see some of them. So here, so the most important ones are Cosmic Explorer in the US and Einstein Telescope in Europe. So Einstein Telescope, well, this is a slightly older figure. I think they are still not confirmed about what the configuration is going to be. But Cosmic Explorer, they are also currently like testing two different designs, 20 kilometer and 40 kilometer. Well, for me personally, it sounds like crazy because already with 4 kilometers, I have seen how many problems there are. Like I'll show you a picture of me at Livingston. So you see the arm going and the earth curves and you have to like, your laser has to go through the diamond. So you have to correct for the curvature of the earth for 4 kilometers. So 40 kilometers, don't even ask like how it works. I have no idea. I'm not an instrumentalist. But there are plans to go all the way from O3. So these are sensitivity curves projected. So O3 is here. So we are here at A plus right now. So there is another run, some improvements after O5, O6 called A sharp. And then beyond A sharp, there will be Voyager, another configuration, going into these Einstein telescope and Cosmic Explorer. So the sensitivity is going to get better and better with incremental betterment in all the designs. And here, I don't know if you can see, so each of these circles actually represent O3, A plus, CE, and so on. So O3 is actually here, and there are a small number of neutron star systems and black hole systems. A plus is here, Voyager, CE, and ET. So you are moving out further into looking out into the universe and you will detect many more sources. So this is what is projected. But remember that these are again dependent on the binary population studies. And since we do not see as many neutron stars as predicted, we think that needs some correction, but okay. But still we think that we will observe many more sources. Other than that, there are a lot of discussions also on space missions currently. So the missions being right now discussed are, for example, the GLOC, Gravitational Wave Lunar Observatory for Cosmology. Here is an animation. Then LGWA, Lunar Gravitational Wave Antenna, which wants to put some, here it's almost not visible. So it wants to put some seismometers on the moon to use the moon as an oscillator. All crazy ideas you can think of. There is also lunar seismic and gravitational antenna. So there are a lot of missions currently, these proposals being considered. Then, again, this I didn't talk about. You have several space missions for binary black holes mostly because these are looking into the decihertz gravitational wave picture, which is slightly lower frequency than LIGO. And LISA Pathfinder mission has already done the technology demonstration. So next step, LISA can fly. I don't know if you have the money. But there are other missions like DESIGO proposed by Japan. I think they are planning to send DESIGO B Pathfinder for testing the technology. From China, the Taiji and Tianjin, they are also being considered. So all of these have, like there are advantages of sending it into space because you don't have as much quantum noise or seismic noise. So you can look at lower frequencies and you can observe sources at lower frequency. In fact, you can even catch binary neutron stars just before they merge. So if they see something, they can tell LIGO, like, look here, merger is coming. So that is also great for early warning studies.
And LIGO change direction.
No, it's underground. We cannot change directions. That's why we need more detectors to, like point towards the sky. Yeah. So again, I talked mostly about terrestrial interferometers and some space interferometers. So here you can see the map of the gravitational wave universe. So we with terrestrial ones, we mostly look at pulsar supernovae. These are my interest. Then space-based can help you look at extreme mass ratio in spirals, compact binary in spirals. So these are also intermediate mass black holes, so more massive black holes. Then I did not talk about the other one, which is radio pulsar timing arrays, again neutron stars. But these are these giant dish radio antennas, which can also observe like the very low frequency, ultra low frequency gravitational waves coming from early universe, Big Bang, and so on. So all of this, is filling up the gravitational map of the universe, somewhat like what was, Galileo's time until now. So hopefully we will see more and more sources and we will have a better picture of the gravitational wave sky. So I think I'm at the end. So just to remind you that gravitational wave is a multidisciplinary field. I am only at one end somewhere here, but you need instrumentation, you need electromagnetic counterparts, multi-messenger astronomy, you need computation, precision measurements, quantum measurements, and so on. So it's hugely multidisciplinary and needs effort from all these fields to make it work. So it's a great opportunity for students. Also, we have a very active, website and social media pages. So if you're following Instagram, Facebook, YouTube, so we have a lot of content on a very simplified way of telling you what gravitational wave science does. We have interviews of women working in this field, which motivates a lot of young girls to come into the field. Podcast interviews of experts. We have student interviews of working or what they recently discovered in the field. We have astrophotography, webinars and contests, and even art, side art and so on. So I'm also chair of outreach for the Rise in India project. So I'm heavily involved in outreach and a bit of it. And just one shot of pictures of me at Livingston. So you can see one of the arms here. It's actually sitting on a marshland. So they told me it even moves when during the rainy season. And you can see here the plaque, which shows the first detection of the gravitational wave motor. We are celebrating the 10th anniversary this year. And they said they are proud that it arrived here earlier than Hanford. Maybe a few milliseconds earlier. Okay, and then this is the control center. You can see the beams inside the two arms. Suspension, so these are the instrumentation. And that's it. So this is my institute and thank you for your
Yeah, thank you so much for a very nice overview.
Yeah.
Can we also detect gravitational waves as follows? Imagine you're observing binary pulsars, you do timing on the binary pulsars, and the gravitational wave passes through the system, and then you see signals in both of them simultaneously.
Oh, you mean, yeah, so these are two different things. Well, I mean, there could also be some lucky coincidence, but ideally there are two different things. Well, this is also always observing the.
But this is a specific way of doing it. Instead of an array of many pulsars, you just look at a binary pulsar. And then we do timing on the binary pulsar, they are very accurate. Right?
Yeah, so the thing is binary pulsars, so the ones that are observed with these radio antennas, they are much before the merger, right? So what you measure there is the orbital shrinkage and other things. The
Yes,
outside.
but I'm not interested in it. You do the timing.
Yeah.
And then you see a change in the timing of both of them simultaneously, just like in light bulb in different parts, different Italy and the one. So you do the timing.
Interferometry of the.
Yeah, it's like interferometry. You
Yeah.
see the change in both of them
They
almost
do that.
simultaneously.
I think they do that already, right? The pulsar timing.
But the light travel time will be very short.
Very
So
short.
you would require the pulse width of the two pulsars would be narrower than the light travel time in mid-peak. So you would detect one pulsation from one neutron star, and then it should end up, as you said, then you would be able to have to see the second one, and those should be separated in such a way that you will be able to see the variation in the pulses of the individual neutron star. So that would be very unique, but very nice actually. If there is a separated binary pulsar, I mean separated enough,
I see.
because the width of the pulsars, pulsations would be an issue, I guess.
Imagine you model the width and then there is something remaining from the model and you see the same.
So it would look like a broadening of an vision.
Because both of them become, oblate at the same time, for example.
Yeah. And yeah, amazing. Yeah. Very short frequency.
Poor man's detector.
Yeah,
Is 4 kilometers, like why are, like India is also 4 kilometers?
Yeah.
Right? Is 4 kilometers the range that it's comes like slowly negligible, if you like make it 10 kilometers, it improves slightly from like 6? Is that why it's only 4 kilometers? Why isn't it like 6?
yeah, so, well, now you heard that we are going towards 2010 or.
Yeah.
something like that. So it's, well, the problem is when you try, I mean, ideally you want to make an optimal compromise, right? So that's what I was saying, so the more curved, like the more bigger you, the bigger you make the detector, you have to correct for curvature here, you need to, the beam to go through it, and you have curvature as well. So there are many more corrections that are going. Also remember that like the suspensions have to be done in such a way that they quickly come back, because even the bigger you make the detector, the more challenging it becomes, but more sensitive. So until remember this design was started, initial LiPo, started in 2010s. So that was the maximum optimal one that could be done. So now that the technology improved and we know how to surpass this quantum noise and other problems and even proteins, and there are many other technologies. So now people are upgrading it to bigger ones. But bigger ones is also problem. Like even Einstein also, like it is being, it's in like some proposed sites are in the border of Netherlands, Germany, and what is that one? France, I think. So it's already like complicated. So find a land where you have 20 kilometers, uninhabited land where there's no heavy mining. So you have to find a problem. I think this for initial LiPo, this was the best. The reason why LiPo India is the same is because we want to keep the same design as LiPo. So the three can form this triangulation, like this ideal, they will work in coalition with each other. So the other ones are smaller, Kagra and World War II.
So you say you basically we need probably a bit more than minute now to say, when it comes to sensitivity, we need to go beyond the truth. You set down methods to overcome that and quantum noise correction.
Yeah.
Can you say more? Yeah.
So there is the new technique called quantum squeezing, which has been tested already and it is used in O4. So the thing is basically they are, the uncertainty principle. So basically they are doing a workaround in such a way that in the frequency required, you have uncertainty in frequency, uncertainty in well, I forgot which one is which one. So I think the uncertainty in one of them is compromised so that it is, well, don't ask me, I'm not the instrumentation person, but I
It's
think
similar to what they do when they do quantum computing. They also need to kind of correct for errors. So
Yeah.
it's similar. You also then have noise, you need to correct them.
Yeah.
So by having redundant information, and then you still kind of keep the information you want.
So basically you have the uncertainty in either say the energy and time or the frequency and or say the position and momentum. So it is done in such a way that one reduces, the other one increases, but it increases in a different domain where you don't need to look at it. Well, the simplest way of putting it. So that's how you circumpass this problem. But yeah, I think there is also a limit to that. Yeah.
Thank you.
Is there a reason why, like for example, I think Cargo India is a properly isolated place, or like somewhere that
Yeah.
there's so much stuff. Why is it still like underground-ish, or I don't know if it is, instead of like being some lift down, like above ground?
Yeah, so it's seismic noise, right?
Right,
Because,
yeah.
like even close to the detectors, there is an area where you cannot drive fast and that. The reason is that seismic noise will distort your
Right.
signal. Yeah. thermal noise, so that's why it's put inside, this isolated chambers and. Yeah, so we have to correct for all of these kind of things. Seismic noise. Yeah, that is another problem. Like say for you build a detector of 20 kilometers, so you're ensuring that in that entire region cannot have any heavy machinery for noise. So we have issues like this when we go to this place, so the local ministers tell us, so did you choose this place because it is backward and you want any development here? So that's tricky because it's true, but yeah.
They probably won't like you.
Okay, any more questions from anyone more?
Thank you. And if anyone was more specific to this question, I'm still around.
Now I know why you kind of arguing to you all the aspects of it.
Hi. Oh, hi. I see. Right.
My colleagues in India also went to because your level.
Okay.
So, would like to pass on your comment.
Definitely, yeah, I'm head of outreach, I'm not a spokesperson, but I'm head of outreach. Hi.
Hello, hi, Isa.
We have a.
I don't have a business card, but I can pass my. Or if you have a business card, I will. Yeah. Yeah. Yeah, I can, or just have.
I will just note down your.
Yeah, it's
O modelleri işte modelleri yapıyor, modelleri bir de spektrum iki kelime ancak işte
Sure, yes. I'm actually in touch with that. Outreach. We just met at the library.
Is that the one?
Big reasons.
So there are some people in the process.
Yeah.
Italy, I think it's.
So, yeah.
Germany, Belgium, and then.
Yes.
One from Saxony.
Yeah. I was just saying. Yeah, that's right.
So are you in touch with the overall organization? Or one of the proposals?
No, not the proposals. I was actually, since I was working in Europe, a lot of my collaborators are from Europe. I was also in the initially Einstein Telescope had a kind of proto collaboration. So I was a member, but now there is, you have to have research units. So now I have been asked to join one of the research units, but since I'm in India, I'm still figuring out whether I join France or Germany. So I will go in October and figure it out, but I'm not yet a formal member. I'm one of these proto members. I'm a member of, I get all the documents, but I'm not in the group.
Yeah.
So, but I'm in contact with the outreach people.
Okay,
Because
yeah.
I know about them. Yeah.
Yeah. Thank you very much. And also thank you for inviting us.
So do you still have time?
Of course.
We'll go for, I got for lunch, if you want to join.
Of course.
Oh.
Yeah.
But I don't know, I mean, there's not much here around campus, there are only a few places. You know, this area is very touristic. Not the best place for people, so maybe, we could go to where the first day again.
Hi, this will thank you very much. I'm sorry, like, I told I was quite late. We were generally version of as late, but I think it's started.
You work directly for the FSC, and so but it's like a, when you do get to technology.
Yeah.
It suggests that.
You don't have that every industry. You have also the select ones.
Yeah, but you want to know about activity or just the way.
So you're doing some project in the Dutch part?
Definitely, so for example, continuous resources. There are several different particles. So I. Yeah, the one that says that I can give. Then we can just, I can.
You find out more than usage. Yeah, for example, with the fencing, or she's not sure that we don't think, that they don't keep the help them.
No, no, it's like my fingers are too. Yeah.
So that's in the you would find out the president.
Don't have by the concept.
Yeah.
No, but that's correct. Also, I'm trying to think of it's so hard. But how I should.
Yeah. Now, there are some horizon programs.
Sure. Sorry, someone else. No. So this week actually. I have
Is it?